Hello, this is Teach Nichols, and this video is on thin film interference. I want to start with a little bit of background refresher from things we've learned about previous waves. The first is that when light crosses the boundary between two media, like all waves, the speed of the wave is going to change. For light, we use the index of refraction variable, or n, to represent the speed of light in a specific medium. But keep in mind that a large N actually means a small v, so you need to remember that when it comes to whether the light wave is speeding up or slowing down. Just like other waves, when light hits the boundary between two media, the wave energy is going to split into parts. We'll have one piece that is reflected back into the original medium and one piece that is transmitted into the new medium. Remember that the transmitted waves are always upright, so you can see that in the drawing to the right. The transmitted wave, if it's a crest going in, then it's going to be a crest coming through the material as well. However, there's some nuances with reflected waves. If the second medium is slower than the first medium, so the n value increases, then the reflection is actually going to be inverted or upside down. However, if the second medium is faster than the original, so the n value is decreasing, then the reflection is going to be upright or no phase shift. So thin film interference is an interference effect that happens when light that is reflected off the front surface of a thin film, like for example, water or soap or oil, like a bubble, and the light that reflects off the back surface. If you look at the diagram underneath, you'll see we have two light rays coming in. A and B are two photons coming in very close to each other in the light wave. And one of those photons is transmitted into the new medium and then reflects back and then transmits. That's photon A. And the other photon happens to reflect off the top surface. So we now have two photons that are back together again, but one of them has actually traveled a larger distance than the other because one of those photons went through the film's thin film before it bounced out and the other one didn't. In addition, we sometimes have phase shifts that are happening depending on whether that thin film is a slower medium or a faster medium than the medium that the light waves start in. So when the two photons start in phase, there is some combination of phase shifts due to the boundaries and a difference in how far those photons went that ends up causing constructive or destructive interference. If this feels like resonance, it's very similar to resonance. You can kind of imagine in your brain the number of inversions kind of act like the end members of the resonance. 0 and 2 kind of like a fixed or a loose boundary, and the math's going to kind of turn out the same way. If there is one inversion at one of the two boundaries of the media, then it's going to act like a fixed loose boundary. And I'll show you some details about that in the next couple slides. These slides are really dense. You don't have to write down everything, just get the basic gist of it and maybe the conclusions at the bottom. So we have our first set of conditions is when we have 0 phase shifts or 2 phase shifts. How does this happen? Well, if the light is constantly speeding up as it goes through the film, so the film is the like middle layer here, right? We start in the top layer, we go to the middle layer, and then there's a layer underneath it. If all of those layers get successively faster as the light wave travels through them, then we never have a phase shift at a boundary. We never invert. So in the drawing on the left, you can see the green waves are basically upright waves. We have an upright reflection off the top boundary. We have an upright transmission that goes into the second medium. We have an upright reflection off the second boundary, and then we continue upright. So these two waves match the phase that they came in with, and they match each other. We also see the same sort of situation if the media are constantly getting slower or denser, because we have phase shifts both at the top boundary and at the bottom boundary, and that basically cancels out the phase shifts and ends me back up where I started. So in this case, you can see the wave inverts at the first boundary and turns into a red wave. The transmitted wave is always upright. Then when we hit that second boundary, which again is getting slower, we invert again at that second boundary, and then we transmit upright. So this time we inverted twice, but we match ourselves because we come out in, both of the waves, the wave off the top boundary and the one off the bottom, um, end up still in phase with each other. So if we have these conditions, then we end up getting constructive interference when the thickness of the film is a multiple of a half a wavelength, just like we get constructive resonance when we have the length of a material is a multiple of a half of the wavelength, right? And the reason is because the path length difference is actually double that. In the first diagram on the left, you can see the wave that went into the film had to go one full wavelength further than the wave that just bounced off that top boundary. And so if there's no inversions and we have one full wavelength shifted, we line up again. We're still going to be constructive. And we get the same thing if that thin film is uh, double that size or any multiple of a half a wavelength. Okay, so the opposite conditions are going to produce destructive interference. We still are dealing with a 0 or 2 phase shifts. We still have the same media, but this time the films are different thicknesses. In that example on the left, or the left of the right part of the screen, um, what we have is a thin film that is a quarter of a wavelength thick. Okay, the reflections are doing the same thing. We're not inverting on any of the reflections, but this time the total path length difference is a half of a wavelength, double the 0.25. We've gone through and back up again. And that means that the crest of the top wave is going to line up with the trough of the wave that sort of went into that film. And so that's going to produce destructive interference. So we're going to notice that we have destructive interference every time the film thickness T is 0.25 wavelengths plus a multiple of a half a wavelength, right? So 0.25, 0.75, 1.25, etc. We didn't really focus on the destructive interference in resonance because it's not that interesting, right? Basically, you have no wave. But in thin film interference, it's going to turn out the destructive interference is really important. So I actually put that in red because these are the numbers you have to keep track of by and large for the test. So the other conditions you can encounter happen when there is one phase shift. One of the two reflections off of either the top surface of the film or the bottom surface are going to cause a flip and the other one is not. So this happens when you either have sort of a slow, fast, slow or fast, slow, fast. On that example on the left, the first boundary speeds up. So we go through upright, we stay green. But the second boundary slows down, and so we invert at that boundary, and then we stay inverted as we transmit. So you'll notice, ultimately, the two waves that are coming back into the original medium are 90 or 180 degrees phase shifted from each other. One is red and the other is green. In the second diagram, we went from a fast to a slow on the top surface of the film, so we actually invert there. But once we get into the film, then we hit the second boundary of the film and we stay upright at that reflection because we're actually speeding up. In any case, the net result is the two waves coming back into the first medium, which are the two that we actually are getting the thin film interference from, are 180 degrees off. So the conditions for constructive and destructive interference are opposite from where they were with the other waves that or other thin films we looked at in the last slide. In this example, you get constructive interference whenever the thin film thickness is a quarter of the wavelength plus a multiple of a half. Because when you add in the half wavelength phase shift, right, that puts us into these categories of, crest and trough lining up. And if we have thin films that are multiples of a half a wavelength, then we're going to get destructive interference because the path length difference lines them up, but then the reflection inverted shifts them off again by 180 degrees. So in any case, when there is this condition being met, a speed up and then a slow down or vice versa, we're going to have destructive interference when the film thickness is a multiple of a half of a wavelength. And again, it's probably going to be primarily those destructive numbers that you're going to need to keep an eye on for this test. So why was I harping on the destructive interference? Why do I think this is the most important of the numbers? Well, it turns out that in the human eye, destructive interference of one color is much more dramatic and obvious than constructive interference. White is all three colors, but if you take away one color, if you take away the blue, for example, then we see a dramatically different color, which is yellow. If we take away the green, we see the magenta. If we take away the red, we see cyan. Um, if we were talking about constructive interference, if one of those colors is constructively interfering, but all the other colors are still present, uh, our brain sees white plus a little bit more. And that's not quite as dramatic as seeing these colors of the rainbow, these yellow, magenta, and cyan. So when we see thin film interference in the real world, we tend to notice the destructive interference or the color bands that match up with destroying one color instead of adding more of another color. Here's a blown up picture of a bubble, and you'll see that the colors that you primarily see in this are the cyan, the yellow, and the magenta. You might see some little bits and pieces of constructive interference and other colors in there, but primarily it's sort of a repeating rainbow of yellow, cyan, and magenta. The top of the bubble doesn't have colors, and that's because it's too thin to interfere in the visible spectrum. We'll probably do some practice on that in class. And after the first set of bands, you'll notice that they repeat over and over and over again, right? That has to do with basically the thickness of the film lining up with conditions to destructively interfere each of those three colors in turn, destructively interfere or destroy the red, destroy the blue, destroy the green, and then it does it again for the higher order interference. So we'll talk more about this and look at examples in class, but this is a typical photograph of something caused by thin film interference. All right. So I don't know that you'll ever look at bubbles the same, but next time you look at a bubble, think about the fact that the colors you're seeing are not caused by a colorful film. They're actually caused by your film destroying the white light that is going in. Thanks for watching.